Yeah.
In April?
End of April, yeah.
Oh,
really?
It's NCC class.
I hope so. I hope
Yeah.
so. I got some of it put together, but there's a big push this month, next in April. Put all the stuff together. I hope.
Yeah.
You never know the first time.
Yeah. Yeah. In the same day, there's some other conference in Houston.
Oh, there is?
Yeah.
Good.
It is just like I think it's some kind of convention. Completion technology for unconventional as well.
Okay, you know who's better. Very good.
So you're in good shape, huh?
I have email, but I didn't check.
I don't know that a lot of people signed up for it.
Yeah, I know, because it's exactly the same dates, from 28 to 30, I think. April 28 to 30. Yeah, so when I talked to Mike, he said that we will send someone to your class and send someone to that class.
Okay.
To that conference.
Well, it's too late to change the dates on ours. We just picked it out of the blue. It was no big deal. But I think it's probably too late to change the dates.
Someone called,
Okay.
but I couldn't figure out how to answer.
Chad will be here.
They hung up.
The thing we're having a problem with is that if people don't have admin rights on their machine, apparently this thing won't load correctly.
Right click on it, say, what is that?
For you, that might work. But for the guy who called in earlier, apparently he had already given blood and was working on the dashboard.
He works for Exxon?
PhD.
Is that head turn?
Sorry?
Head turn?
No, Rick Marquardt.
Oh.
So yes, he's Exxon.
But you wouldn't think that if on the computer rules will.
Well, BHP is run by Exxon. How's your new life, Steve?
Pretty good.
30 years of marathons, just what?
20 now was plenty. Yeah, I'm old from Well's going back.
You'll be reaching your Amico best. Was there in 2013 or 2014?
Oh, yeah, I'm way past it. Yeah, my retirement starts to become less valuable.
Sorry?
My retirement is becoming less valuable every day.
Well, that's true no matter what. Well, Aramco's here. I mean, Halliburton.
A little of both. How you doing?
So this is the health food, right? Yeah. I just wanted to make sure. Currently, we have. Yes. Oh, you didn't know this? I'm good. This is Mark. That's going to run our IT for us. Not sure what to say, because I don't know. You want to check your email real quick, see if you got it.
When you leave the ransom, do the new company?
Where's your money plug in?
Oh, September.
Yeah, September 1st. I took vacation over August. Most all. So, yeah, I left
Okay, so
Because I remember last time I saw you was dealing with
who asked that
medical.
question earlier? The smart ass answer to the closest restroom. Oh, it's right there. Is that when you said women on it? The one next to it is the one you want. And remember, this is student floor, so you might want to wear some hazmat gear when you go in.
I really kind of wanted to work till we
This time of day it's probably okay, but
Yeah, it was.
it wasn't part of the plan.
Considering.
So how is your new company?
We're drilling some wells up here.
only,
So we're a private
They got 11.
unfortunately,
Totally how many
we just
employees?
affected
9
staff and well,
Did you expect to expand?
It depends on what the company looks like
They
this
said,
time next year.
I know to everybody
Yeah,
who was
if we're in development mode,
we always try to be nice when it's not so good. We're going to have to stay about
it's small. The business model is not ever to get too big.
well, you're going to put your name down.
One geologist, one reservoir engineer, one drilling,
Or you want me to grab some cups?
a land
Well, I'll go get some more, but I was wondering where I could put it, but I guess
Some
they'll sit right there.
Yeah, that's
All right, I'm gonna get you more water than
Yes.
this.
There's the president.
Okay?
reload water.
I'm gonna
But it's
do the-
fun to work with you.
Yeah.
Yeah.
Yeah, it's a completely different thing.
Very important. But don't get between Dr. Poe and the donuts. Come on.
Okay, I will.
It's fun. It's a little scary. You're the only one, right?
Yeah, everything that on your left.
Councilor Lynn?
Ted, you want to explain, I don't think anybody here is using technology, but you want to explain to them how to get online if they want it. Does anybody else need it here?
Exactly.
We will have wireless access available shortly. I have to get the specific user account information from CIS on campus.
We could just grab a couple more wires. We've got plenty of outlets
We can
here
do that too.
and here.
Sure.
Why don't we just do that? I don't think anybody here is going to. Anyway.
I think I can put
There was a specific question. I don't have the information right now. So I have to figure it out.
What's that?
He wants the actual IP address to the Bridget server.
Be notified.
Yeah.
The other thing is, how do we get this out of the way? I don't want to close it. So just pull it over here.
Yeah, sure.
Just put it right on the end. I guess I can leave that
That'll
on.
stay there unless you want to close it.
And the Bridget doesn't show up down here.
Yeah.
I can probably leave it like that for me.
Yeah, Hank's got it.
So you have to close it if you need to.
Yeah.
I won't close
Let me
it.
have the. Oh, okay. Back and forth.
Thanks again for all your help.
Sure.
Okay.
This thing turns red when the battery runs out.
Yes.
Mayor Hopper, okay, good.
right, it's time to get started. So coffee is over here. Laura's filling up the tank. Why don't we give you guys an opportunity? Anybody want a coffee? No? All right. So we're going ahead and get started. I think probably have 2 or 3 more people trickling in, and then we've got some folks online. And again, the online part, some people are having problems with the admin. All of this will be recorded. There will be a 2-minute gap between the all-day videos. I think it goes 2.5 hours and then takes a gap. So just FYI, we'll put that somewhere once we're done where you can get access to it. And I think that's just about everything I can think of. So, it's a small group. Let's all introduce ourselves. I'm Tom Blassingham. I'm with Texas A&M. Matt Reagan. Matt, you want to introduce yourself?
I'm Matt Reagan from Berkeley Lab. George Maritas will be here shortly. Just want to actually say up front, this work that's being presented was funded by a 3.5 year project funded by RIPC, and we'd like to thank them for their sponsorship and support in putting this together. I'm a research scientist at Berkeley Lab and on reservoir engineering in primarily shales and hydrates.
Matt's a scientist. Okay. He's technically an engineer. But that 3-letter school you went to, right? Stuart, you want to take over next?
Sure. I'm Stuart Cox. I'm with Petroleum Engineering.
Herb, you want to rotate?
I'm Herb Sebastian. I'm a reservoir engineer with BP in Houston.
Greg?
Greg Sapola, Senior Completion Engineering Advisor with TESS Houston.
Bob Gould, Interpretation Engineering Advisor with Houston.
David Fulford, a reservoir engineer with Apache.
Mark Pruitt, I'm a reservoir engineer for Aramco Services Houston.
Yan Chen, R&D Supervisor, Steam Lab, Division Collector.
Mark, you left out your most famous accomplishment.
I've been credited to some degree with inventing the Dustbuster.
Yeah. Isn't that cool?
So if you look up on
Wikipedia,
which is the most reliable source you know of.
Yeah, I've only been credited with inventing mayhem. So, well, okay, we'll go on ahead and get started then. And I don't know who else has got control of the screen, but they need to let me have it. I'm going to work from a PDF, as you can see over here. And this particular project, you have to swallow a frog to get it all out. The lab likes acronyms, and this one in particular was focusing on the geophysical, geomechanical, and geochemical aspects of shale and tight gas production. We did not have a field demonstration as expected. We did recently close a negotiation with a company to get some data, but I think that was a little bit after the fact. We had an initial partner, but for some reason the federal government didn't like spending money in Canada, so that didn't go anywhere. I guess, Matt, if you want to give a quick thumbnail, we started roughly 2011, if I remember right.
This project started after contracts and everything was put together. We started in June of 2010 on a 3-year project, which we extended to basically a year and a half through December 2013. And this was a joint proposal, $2.9 million funding groups at Berkeley Lab, Tom Blasingham's group here at Texas A&M, and Mark Zobak's group at Stanford. And everyone was able to sort of work in their individual field. And today we present the combined results and hopefully put it in a larger context. And I think what we want to accomplish here today is RIPC has a requirement that we communicate the results to the public and industry. And we have quite a number of papers coming out of this, but I think it's even more instructive to get people who are interested together in one room, do these short presentations, and then have opportunities for discussion, and maybe future talks or collaborations. Thanks everyone for coming.
Yeah, I think the other thing I might add is that for us at least, Erdal's got the mouse. Erdal, let go. The project for us anyway generated an enormous amount of student activity, which was not really what we had intended. I know that's what we had put down on paper, but to give you a thumbnail sketch, we've got a ton of student projects on this. The geomechanical aspects of it were never really realized until the last couple of students, but a lot of things that would affect geomechanical aspects, the modeling, some shortcut solutions, some things that you'll recognize, they were all part of this. There was a ton of modeling, looking at variations in well geometries and that sort of thing. And you may say, well, this is kind of interesting, but why did you do this? The reason we did this is we wanted to eliminate things that probably weren't going to be practical for well stimulation in tight gas and shales. So I guess with no further ado, since we need to stay on schedule, I'll go ahead and start. This is our agenda for us. And again, everything today is being recorded. I'm going to give all the presentations except for the last one. I would also prefer, if George is here, that he give the presentation for Dr. Yang. It is material that I'm familiar with, but definitely not my expertise. That's the one at 11 o'clock. We probably will finish this section early. There are 6 slides per section, and unless I talk slow or you ask a lot of questions, we're probably going to get through this pretty fast. So I don't think anybody will complain about that. And obviously, interrupt me at any time. Interrupt Matt. Matt today is Mark Zobak, so if you're wondering why he doesn't look as tall as Mark, well, he's doing an impression or an impersonation. So any questions before we start? Again, everything that we have will be posted online for you. We'll probably post the PDFs. I did post the PPT of mine, but I'll probably pull it off. Just as a rule, I kind of don't do PPTs because then people steal your stuff and go, hey, I want to know more about this. And you're like, no. So, Matt, I don't know, do you have permission? I guess you have permission to post PDF, so we'll do that.
And actually, if you guys don't have facilities, we have a server at the lab.
We'll do both. We'll put it on a public site and stick it out there. I'll probably create a download link on my main drive for this, and then you guys do the same. Now, the videos are going to be large. They're usually on the order of 1 to 2 megabytes per minute. So just FYI on that. They should be WMV, so they should be, or no, sorry, they'll be MV4. MV4, which will be picked up by your Windows Media Player, I believe. Any questions, any other concerns before we start?
The stuff in parentheses, Freeman Hill Corp, is that?
That's where the student is now. Sorry, thank you. Yeah, so Freeman's at Hillcourt, Oloroto is at Afrin, Otonowo is at D&M, et cetera, et cetera. And the last guy is still here, so he's working on some interesting things. Unfortunately, he's at the start, and he's also probably the shyest guy in the group, so when he gets here, beat him up a little bit. He's Polytechnique grad, so he can take it. Okay, so again, this is Matt Freeman's work from his master's thesis, actually, and as Matt pointed out, this sort of overlapped time-wise, and it also, the reason we're showing this now is that it set the stage for a lot of the other modeling. A lot of the work that Matt Freeman did enabled the work that other people did, so that's why we're going to talk about that today. And one of the things, and I wish George were here to explain it, but one of the things that Matt did that was a bit unique for us is he was using million cell models on the multiple meter scale, like 3 to 5 meters, so it was a lot of cells looking at things like desorption, things like pressure gradients and so forth. And we're not going to debate whether or not you should represent a fracture in a shale with a plane or that sort of thing. What we were trying to do was establish numerically what this would look like, and then also possibly what it might mean for reservoir engineering aspects. And again, Matt segregated his model into these different components. We had to break it down into which types of fractures there would be, which types of dual porosity connections, and so forth. So in a sense, every possible combination, or every likely combination, I should say, is being included here in terms of these components. And again, all of them are connected for modeling purposes. His thesis was much more exhaustive than the 6 slides I'll show here, but the goal of this was to present all these different options in terms of how they might behave. So George is here now. This is George's domain. We had Matt create a horizontal multi-frac well model, extremely high resolution. We were looking at stencils, which are these elements, if you want to call it that. And of course, what we did was we established the basis for using elements and then validated the concept of using an element. And then, like I said, Matt generated like a million cell model or multi-million cell model for this in order to see the intricate pressure gradients, desorption gradients, and their influence on production. I mean, we had some bumps because we were not particularly, we didn't have anything to go on. We were using our own intuition and our own knowledge. Matt's thesis, as I mentioned, is much more exhaustive. We went into Knudsen flow and into some other phenomenological type behaviors into here, but all we're really showing today is gross, sort of looking at it from this standpoint. In a way, again, this set the stage for other things we wanted to do, and it was quite innovative at the time. This work gets a lot of references in the literature. I wish, frankly, it had been published, but SBE didn't like it. So
it was published.
Yeah, I know, but not in SBE. You may want to introduce yourself.
Hello, I'm George Moridis. I was the overall manager of this project. I apologize for my lateness, but some sartorial accidents I had prevented me from being here earlier. What Tom is showing you right now is a very high definition numerical simulation study of flow behavior through a wide range of possible occurrences of fractures in porous media. And, well, as you will see later on, this formed the basis for quite a few of our studies.
And again, what we were trying to do here was demonstrate the extreme pressure gradients near the fractures. The horizontal well in this case is also on, but it's not a significant contributor. There are other cases where the horizontal well is not on, just the fractures themselves. Obviously, we began looking at a quadrant of it to save computational time. The important thing here is, again, the extreme gradients that you're seeing near the fracture. Now, I'm not going to debate here whether this is representative of everything we see in the formation, but the goal of this, again, almost 5 years ago, was just to see what this looked like. So this was sort of the starting of the base, and then we started looking at desorption and density. And what we were really trying to understand was what was a desorptive component. I know everyone in this group to some degree. If I were to do a quiz and ask you what you thought the contribution of desorption would be, let me go on ahead, Craig, I'll call on you since we get along better than everybody else. Do you think desorption is going to be a serious component of production? Three options, right? Yes, no, or maybe?
Not in the early time.
Okay. Well, and that's what the results show. Those black, red, and blue lines show that there's essentially no contribution in early time. It happens later on. And what we found was that the shape of the curve implies what? Well, they're all the same. So they just be shifted for some part. I attended a conference with a I don't know how to put this politely, a very mature contributor to the petroleum literature who's probably now left the business, if not the planet. And his comment was he would be really surprised if shales contributed more than 10% desorbed gas. Now, if I did a poll of each of you and your plays, you might have other numbers. But it's not going to be 80%. And it's probably not going to be 50%. And what this tells us is it's probably on the order of 15 to 20%. And of course, all of this comes from our modeling, not from actual understanding. So Matt spent an inordinate amount of time trying to calibrate and make sure that what we were producing in terms of these desorption maps was representative. And again, we wanted people to understand, as Craig pointed out, exactly, it's a perfect lead, that this is not an effect that we're going to see during early production. So. And then to close out this, we did start some work on mix and flow, and you can see what happens is as you lower the pressure, the permeability increases. This is a nuisance flow phenomenon. So we had done a bunch of modeling with this as well. This is all in this thesis. But what we really wanted to understand is what we would expect to see in terms of performance. Now, if I do a poll in this room and ask you, why does shale gas look like it has Darcian flow behavior, what's the answer going to be? Sorry, because that's what we want. That's actually what mine was, is that's what we want to see, so that is what we see. But we should see other features here. We should see things that perhaps don't make as much sense, especially if we include the foundational behavior like mix and flow. There's been several papers since this on modeling with these nanoscale or attoscale type features. There's still a lot of work being done on this. You know, guys, we're at the beginning. This is the first talk of the day. I don't want to muddy the water, but I think there's still an enormous amount of unknowns. The questions that are raised by this kind of work are still valid today. We don't really know the answers. So, you know, this is something we have to continue to focus on. Now, later on in the discussion, we'll talk about multiple fractures and how we may see this create some sort of an effective medium. Our group has not studied that per se. We did do a little bit of work in a fractal medium. The student that you'll see speak last in this particular group, he also is going to show you some multiple fracture, some random fracture type characterizations. We're at the beginning of that work. What I want to do is see if that characterizes the same as this. Unfortunately, that is extremely computationally intensive, like days to complete, because we allow the fractures to propagate randomly, and the simulation grid that results from that is enormously inefficient cost-wise in terms of computations. So we'll leave Mr. Freeman for now. We'll come back to him later. This is essentially a project that was dictated by Dr. Morides, and I want to say that there are some foundational things that are answered here. Dr. Morides is an extraordinary mentor. He seems to take average people and make them very good people and make them outstanding. I'd probably be evidence of that, but I wasn't a student. Femi began this project, I think, not really sure of where it would take him. And what he was looking at in simple terms was non-orthogonal fractures. And what I asked for later was not only non-orthogonal fractures, but to have a horizontal plane or multiple horizontal planes in that. And my aha moment with this, and I'm giving away the secret, I apologize, is that non-orthogonal fractures behave like orthogonal fractures. The production does. So maybe that helps us to understand this. Of course, it really depends on surface area, and there are some aspects of non-orthogonal fractures that if you change the conductivity, it behaves a certain way. But the aha moment for me was when we put the horizontal fractures in, and all of a sudden we got some really interesting behavior in terms of rate and pressure, and it started matching things that I see in the field. And I'm like everybody else. When I see something that matches something that or I see a model that matches something that I observed, I want to immediately jump to that. So I apologize in advance. Whenever we get to the closure of this work, you're going to see me say, this is my aha moment, this is what I believe has happened. David, you recently wrote a paper on observation of linear flow, and how you utilize that, and so forth. What would happen to your model if instead of having linear flow, you had another power law regime? Probably not a lot. You could modify it for that. You could do that. But what if it switched from linear to something else, and you could physically observe that? And we're talking about all transient behavior, not post-transient behavior. So,
well, if you're able to describe it with a hyperbolic model, it still works.
correct, and there will be some positive discussion about that this observation that we'll show at the end, and again, they're model results, so they're not, shouldn't give them too much weight, but what they tell us is at least the observations we see in the field and the model results sort of overlay, and we can make some conjecture about that. And so the things that we're doing to characterize rate maybe is okay. But what does it mean when you start seeing multiple power law regimes in a single trace? That's what I'm trying to understand. Is it a dual porosity system? Is it some sort of a fracture network? Craig, you guys did the first work on this where you were modeling multi-porosity systems numerically. Some of your results suggested the same thing. I don't think you were looking at quite the same kinds of structure that we are, but people want answers to this. And again, as part of this project, it was to understand the behavior. Now, geomechanically, how that's created is another story. So.
But there is a lot of people suggesting that we have horizontal components in these.
Correct.
Horizontal.
And after you see this, you're going to go away going, I believe. And unfortunately, you have to temper that with the geology has to support that belief. Where I'm at right now is it has to be a formation that has a weakness plane. Now, I'm telling you your business, but we know there are several that have a weakness plane that a horizontal fracture could form. And in particular, I was looking at this and thinking that I was seeing the answer to Haynesville and Marsalis. But I could be wrong. So again, the non-orthogonal or zigzag type fractures, and we did not program this to the point where they could all go off in different directions and different behaviors. There are people who've done planar fractures that do go off in different directions and so forth. These are just simply non-planar, non-orthogonal. And George, if I misspeak on any of this, please correct me. But essentially what we found is that it's a surface area that controls everything, so as you would expect. So Femi did an awful lot of work on gridding, and that's what we're looking at next. George, I'll let you insert anything you want to talk about here, but
before you start showing the Q versus T graphs.
But I think we're comfortable that this is extremely high resolution gridding, and we're comfortable that the results we're seeing represent the physical scenario that we're proposing. So as we go through this some more, as George was just implying, here's a case of non-orthogonal fractures, and you can see that we do have perhaps a slight early time numerical effect. This would be fracture flow type effect, not something we'd see in practice. Then we see our characteristic behavior, and you can see there's multiple planar fractures in these two cases, and then there's non-planar and non-orthogonal. And I know you're going to go, Tom, that's not exactly the same as the black and the green line. But if you were looking at physical data, you couldn't tell the difference. So, and then we actually all converge, and then of course we go into whatever this transition regime is between the fracture system and the non-fractured part of the system. So from my position, non-orthogonal, orthogonal, non-planar, planar, practical aspects are going to look pretty much the same. We may be able to step back 5 years from now and say, okay, we need to have a model that represents this non-orthogonality, non-planar. But David is someone who just worked on this problem. Does this really look out of bounds for you? No, because your model would capture that in terms of data noise or nothing, you know, however you want to look at it. Well, I'm sorry, I don't mean data noise, but it would treat sort of unexpected behavior, and it would just go ahead and fit that. Okay. So the next slide on this is explaining the cumulative production behavior, and I threw this in just so you would see that, you know, there are some advantages, but I think these advantages are all due to surface area. So whenever you see more surface area, you'll see more production. The last slide in this, or the last two slides, is when we put the horizontal fractures in, and I'm pretty much going to focus only on the single horizontal fracture case, but you can focus on whatever you want. The horizontal fracture can be in the plane with the well, it can be not in the plane with the well, there can be multiple horizontal fractures. You can see the grid box for this is horrendous, and there's a lot of work that went into this. I think Femi probably wanted me dead well before my time for having him do this. And we had some other people working on the meshing part of this as well. So this is what you came to see, and I apologize, we don't have, do we have tools here? Yeah. So there's your linear flow. And what's going to be next, David?
Transitionary, or
what about 2 to 3? Is it 2 to 3 or 3 to 2 or?
well, I mean, if we're talking about
That one didn't match. Does it?
what I see is what determines is more a function of your well spacing than anything else.
Okay, but if you were to look at this, what would the slope be on these?
Well, this would be a fracture space.
So that looks like, trying to get in my head what this, no, it's not a half, it's,
Line's pretty close to that.
I did this right, huh? I'm losing my mind. Okay, so that's a half.
That's the upper curve.
Yeah.
Lower than that.
Yeah, I'm trying to get into this, what I think, it's 1/3. Yeah, that's what I was trying to do, sorry. There's 1/3 slope. So 1/3 might be a transition regime for having multiple fractures. And that looks a little dramatic. I had a case. No, it's 1/3. Okay. What would that imply? Well, it could imply if we see a 1/3 slope or something less than a half slope, could be finite conductivity fractures, which we all looked at before. And this variation, what I'm thinking is that it's probably a component of the horizontal fractures, and those horizontal fractures, add energy to the system or add rate to the system in this form. Where I was really looking for this is I saw it in some more solids production. So if you have an opportunity to go back and look at your Marsalis production and you're seeing non-half slope behavior, this might be an answer for you. But it's just a point.
Tom, when you guys did all this modeling, what kind of conductivities did you put in these various fractures?
You can see them over to the side. Unfortunately, the CFDs don't make a lot of sense, but the CFs are there. They're 400, 300, 100, 30, 16, 1.6. These are all metric conversion type numbers, and so on, and then working your way down. So the column that Craig's asking about is here.
So how much difference, what you're seeing in the transition regime, like you're calling 1/3 slope, how different would that be between,
You're right.
between a matchstick model and a slab model, or a stratum model and dual porosity?
Both points are right.
They play on it, I think.
And I'm not going to dispute that.
The geometry
I saw what I wanted to see, which was that horizontal fractures gave me an answer for why I was observing that slope. But you're absolutely right that this could as well be a dual porosity feature.
It's exactly the same configuration.
And this is a uniform or constant conductivity in all directions?
Yes.
Okay.
That's another issue as well. It could be differential conductivity effect. So there's multiple explanations for this, but until we had modeled this planar horizontal fracture, I'd never seen this behavior before. And again, you know, my line isn't very convincing up there, but I began to see a lot of cases like this and was trying to understand this. Now, I'm sure everybody in here is thinking, okay, Marsalis is probably, it's a dual porosity part, and I won't dispute that, but I also saw this for...
It's not on your slide, your geometry, your fracture, you have your fracture set up, it looks exactly like a matchstick model. The results should be like a matchstick model.
Could be. Yes, George?
The point I'd like to make is that in a project I'm working right now with the Gas Technology Institute, with lots of data from ourselves, we see this non-1/2 behavior quite often. And actually, as part of this Femi study thesis, he did quite a bit of variation of the angle of the fracture. And he showed the slope change with the angle of the fracture. So at least mathematically, physically, there is a sound basis for that. This may not be the only reason for the excursion from the -1/2, but certainly I'm convinced that it is a contributor.
I mean, we haven't even begun to start talking about when we're looking at, you know, dendritic. I know that word makes a lot of people uncomfortable, but when we look at sort of fracture, you know, typical fracture concept behavior, but any one of these explanations, like George is saying, being off trend, or Bobby's saying being a dual porosity, Craig saying the same thing, and then I'm suggesting that this horizontal plane could be an equal contributor.
By the way, the dual porosity issue that Bobby raised, quite a few of these simulations were running with the assumption of dual porosity anyway. So it was not assumed that in all cases that the matrix was just a uniform block. It was treated as a dual porosity system. And we still saw that effect.
But like just the
But
geometry,
you're
the way
putting
it's
up-
set up,
Putting up fractures in it.
it's the same thing, it's dual porosity, the same way.
Well, there are the options that we have is to run the force medium either as a uniform system or as the sum of the fractures and the matrix, which is, you know, actually it was a bit more complicated than dual porosity, given when the dual permeability system, and we still saw the variation of the slope as a function of the angle of the fracture.
But these three guys are also doing that kind of modeling, and
Okay.
but we did it with our own. We did it with ultra high resolution gridding. We're trying to eliminate all those other things. So now we're going to move out of something that's a little bit discretionary, let's say, into something that's going to be probably the funnest thing we do today. So let's pretend that Dr. Pruitt decides he is going to create a new well model, and he is going to go out and he's going to try to get financing for his new well model. What kind of well model would you create if you were going to do something completely new?
Modified zipper fracture.
Okay, so that would be an excursion into using something that we do existing and create something new. Now, if you did that and then drilled a horizontal well in between it, and then, you know, did something else there, that would be a new model, and you'd go out and you tell your former employer that I want to get rich by you investing in my idea and so forth. I need to be careful because it's a public forum, it's being recorded, but someone proposed that you drill a slot in the formation. And they proposed this in several forums. They got some funding for some preliminary studies. And I still remember Dr. Merides came to my office and he said, either this works or it doesn't. I don't think it does, but we're going to study. And so we spent a student on studying the slot drill concept. Now, I'm not debating whether the slot drill can be done or not. In a moment, I'll show you that. I just want to get a poll of the people in this room. Do you think if you can create a horizontal plane 1/2 inch wide in the formation, that it's going to be competitive with a horizontal multi-frac well? Yes, no, or maybe?
Create the surface area, you should be able to direct it.
Yes.
Maybe.
Maybe. If you guess wrong,
I
no
would
answer.
worry about geomechanical failure without anything to hold it.
Okay. The young always get a vote. Next.
Yeah, if you create the surface area, you should be able to drain it.
Okay. But as David's pointing out, you're going to have to pack it with something to keep it from closing. And we're not discussing that today. Greg, you get last word.
No,
Will not work. It will not be competitive.
that's my vote.
Okay.
Before you go off on this one, on the last one, did you change the angle of the horizontal fracture?
We haven't done that, no. Great question. Okay, so, and again, I'm not debating whether this concept works or not. I'm just here to give you the message.
Just a comment, Tom, I mean, isn't this the same thing as longitudinal fracs?
It could be the same thing as longitudinal fracs, and it could be the same thing as a lot of things.
I guess it depends on how many times you do this.
I have to say that you have the option of directing the direction of controlling the direction of the plane. So you can make it vertical, you can make it horizontal, you can do whatever you want. Well, that's what Carter.
We'll say. All right, but the point is this is the same as longitudinal fracture. And so you've already answered your question that a longitudinal fracture will not be competitive. A single longitudinal fracture will not be competitive with a horizontal multi-frac. You've probably done that study 100 times, okay? His contention is you can put this anywhere you want, just like George said. So whether that's true or not, we don't know. I'm sure by now he's patenting this process. But our goal as public servants, if you want to call it that, with public money, was just to see if it worked. And that was it. So the student studied every conceivable aspect of this. And sorry, I already jumped to this. There's about 50 slides in this package. And one of them was creating a bow-type grid. The other was creating sort of a skewed bow-type grid. And you'll see him referring to it in the thesis and in the other parts of this work as an approximate SD. An approximate SD is your longitudinal fracture. He just got tired of trying to make it into some sort of an arc, so he just made a rectangle. And I'm gonna say that's okay.
How deep is this slot? How deep is this slot?
We think the width of the slot would be the width of the cable, which would be 1/2 inch. But as David, how deep? He claims it can go to China. No offense, but I mean he claims he can do it at depth. So I don't know.
So you get the thing drawn here. You're expecting the cable to be creating like a vertical, like a longitudinal fracture. What if you had this wellbore in a 1/2 arc horizontal plane, and you're pulling that cable, you can make a horizontal fracture out of it.
Yeah.
A horizontal drain hole. Yeah.
He has proposed and patented all of this, but I don't think it's been delivered yet. Did you guys already buy this company?
Not that I'm aware of.
But I think I'm like Craig, I mean, my parents named me right because I first saw this and I thought, at best, this is going to be a completion nightmare. At worst, it's not going to do what it's going to do. But if you look at his graphics, he makes like a daisy flower arrangements, and he makes, you know, multiple where you have radial arms going out, and you do this. My fear is if you lost the equipment, you lose the well. But you know, that's negative. Let's be positive. This was a great question for an academic study, so that's what we did.
There are other additional positives of this here, of these promising issues. Number one, the amount of water needed for this is basically minimal. So that is, the environmental issues becoming an important consideration. So that added to the, I guess, to the appeal of this potential technology. In addition to this, theoretically, far more control than you have over conventional multi-stage fracking. So this being the case, we simply could not have escaped investigating this issue. It was too interesting and too exotic for us to not do it.
And we're happy to say that if you're able to deliver this and you want to repeat it, yeah, it could theoretically be competitive. But drilling time plus other operational issues, I think you're looking at a very difficult challenge here.
Well, we're thinking about the future.
So the first thing he did, and apologies, he called it a straight horizontal well, but this is an unfractured horizontal well, so this would be your base case, Craig, without a longitudinal fracture, if you want to think about it that way. The next is he keeps calling it the approximate slot drill, but it's just a high conductivity rectangle through the formation. And then the next is the multi-stage or multi-fracture horizontal well case. And here's the end of the story.
Let me interject something. He did the full description of the full slotted system with the curvature.
Yeah, he did.
And the reason why he went then to the simplified is because he found out the differences are really minimal.
But the computational nightmare that he had to do for the bow.
I mean, I have to say that both he and the previous guy, when we came here, when I asked them if they know Fortran, they said no, but we have Microsoft Word, will that work? So they had absolutely no idea about modeling. And they were both, right? They just took it like duck to water. And all of these involved supercomputer simulations because there was only easily between 2 to 5 million equations.
Well, I could tell an equally interesting story. I remember the first day of class when I taught them, and they were really not prepared, but they both did a phenomenal job of catch-up. Pretty good in mine, but George really got them out of their shell. You can see that the slot drill has this huge decline. Of course, that's your half-inch fracture depleting, and then it goes into, that's the green curve, it goes into a normal sort of.
I'm looking at the bottom scale there where it says time in days.
Yeah.
My eyes are not that good, but.
Yeah, this is an extremely small time effect.
That's what I'm seeing there. After a short period of time where it's not a
Oh no. This is a startup effect, Bobby. This is that fracture depleting inside itself. This is a half-inch wide, 1,000-meter reservoir, and this is the rate profile. I mean, it's meaningless. We should have taken this off. It just.
Well, it is a matter. I mean, this is basically a couple of hours maximum. Okay, that's about. In essence, you drain the fracture. That's it. That's why you see this very, very steep decline because there's absolutely no resistance to flow.
Sorry, Bobby, you were saying as well.
I'm thinking of a different type of completion, like in these cones where they drill a vertical pilot well and they walk in different directions. There's a company that does that.
Yeah.
Doing horizontal laterals away from the borehole.
Yeah, that's different. That's different.
But he's also proposed that where you would drill radially out and then pull the thing up, and you'd have a bunch of cuts through the formation. The blue has a little bit of a numerical effect as well, but you can see it's the traditional horizontal multi-frac well solution, and then you have the non-fractured horizontal well solution. And of course, the multi-stage horizontal well, it wins. And we tried variations of properties, we tried variations of conductivity, we tried variations of fluid types, and I just mean changing the viscosity, changing compressibility, and it's obvious it always wins. So
basically, after that very large fracture, cranes, then you can see the rest of it is very similar in terms of behavior. Yeah. And if anything else, the surface area here is smaller than the surface area you get from hydraulic fracture. That's why. So this is log, so you can see that.
And for those of you who don't like rate lines, here's cumulative, and you know, the horizontal well just the multi-frac horizontal well is always going to win. He also did a combination case, which was a horizontal multi-frac well with your longitudinal fractures. So it would be transverse fractures and longitudinal fracture, and it had a little bit of advantage, but it evened out in the end. So even, you know, what he was trying to do is say, okay, let's be generous, and I remember this conversation actually, George. Let's give them the horizontal multi-frac well and the slot drill at the same time and see what happens. And let's say you did a horizontal multi-frac, you didn't like the way it turned out, and then you went back and did slot drill. You know, it's not going to be significantly different than horizontal multi-frac. But obviously, you know, cumulative production, horizontal multi-frac well is going to win. Now, these times are so large, obviously, you know, it could go out that far. Everything could work, but you know, your money-making time is back in here somewhere. I mean, this is 400,000 days. This is 600,000 days. Sorry about the scaling, but you know, where you're looking at making your money back is probably back in here. So now we'll take a deep breath, and Dr. Poe, you're welcome to get up here and give this one. This is an interesting one. This one is completely at the insistence, inception, and persistence of the student. What the student wanted to do was use fractal theory to represent a finite conductivity vertical fracture, just a simple case. And he wanted to represent it using the radial flow geometry with a fractal system. Has this been done before? Not to our knowledge. How would you treat this if the student came to you and wanted to do this? Stuart? He wants to take a radial flow system, apply a fractal theory to it to get a fractured well. Hurt? Why not?
What's the basis?
Mark?
What's the basis?
He thought it would be faster. You know. Anybody else? Bobby? You and I worked on this problem. You've spent 25 years on this problem.
It's uniform flux or infinite conductivity. I can see you can readily do it. Finite conductivity has another component.
Yeah. Craig, any ideas?
I'm already confused.
Okay, so you've got the fractured well case, the plane, and what the student wants to do is take the vertical well, unfractured well case, apply a fractal theory to it, and somehow, you know, make this look like that.
So when I see things like this, the only thing I struggle with is how is this connected to it with the reality of the situations? You know, how do we connect this type of approach to the actual completion? Can we do that? It's more of a question, maybe.
Do you think somewhere along the line maybe we had the same parents? Were you adopted or something like that? I don't know. That's exactly the argument I gave him. As an exercise, I didn't think it was a problem. George was much more enthusiastic about it because we thought it might open the door to representing some other scenarios. Everybody who's listening to my voice right now needs to understand this has to be calibrated. It will not work blindly. You cannot take this plus this to equal that without some sort of calibration. Now, maybe there's a process later where we'll be able to do that, and that's why work like this should be done. But in the end, what happened? In the end, we correlated the fractal parameters to the fractured well solution and then put those back into the solution. So the fractal solution was calibrated, okay,
Can you do something?
fancy word, curve fit. It was curve fit to the fracture solution.
Can you do something with a neural network? I mean, did you
It probably would have been just as interesting to have done that. quite frankly.
Even faster, too.
And whenever I show you this, you have to understand that the last slides, well, I won't give away the secret, but the last slides will be interesting, and I want you to remember what you said, and let's come back to that, because that might be a good idea. Okay.
The interesting thing we have to say that is, despite our potential expression of enthusiasm, we still had serious doubts. And as they say, in my adopted state of excess, we was wrong.
I mean, he was very persistent, and there are things that we're leaving out in this presentation and in this discussion where I had to physically sit down with him and explain the only way this is going to work is if you calibrate it. And when we intended to publish it, we had somebody who knew what they were talking about who reviewed it, and they pointed out that the flow scenario generated by a fractal system is completely different than a flow scenario generated by a fractured well. And you know, how did you make this work? That was their question. And we had a little bit of friction because we didn't answer that question correctly the first couple of times, but eventually we got there. So, George insisted that the student prove that he could model the fractal system, and in this case the fractal system was varying porosity and permeability, that he could do it numerically, and with an analytical solution, and you can see this. This is not a calibration of our fractured well problem. This is simply showing that his numerical model that he created could match either the fractal solution or the other scenario. So the goal of this, he was calibrating his numerical model. Everything that we do with a student that has an analytical solution, there's a backup that's a numerical solution. I'm the analytical guy, George is the numerical guy, so everything we do has a numerical backup. Go ahead, George.
The important issue about this is that the numerical model describes a system you understand. So in essence, what you see over here is the equivalence between the numerical model that describes reality the way we perceive it and the fractal approach. You can see that, what can I say? It's like playing poker and someone tells you, royal flush, okay, that's it, okay, you win.
But this is not the geometry we were studying. We then went to the next geometry to study that. But in terms of a calibration, no argument. This worked fine. So the next slide describes the process by which we proceeded with this. And you can see on the bottom, there's a couple of guys in this room. There was a solution by Lee and Brokenbow in 86, and then Cinco in 78 and 86, and then Gringarten et al. In 74. And you can see what we wanted to do, or what was done, was Lee and Brokenbow approximated Cinco, and then Bobby and I came up with a solution that was essentially a direct solution, but it also had to be calibrated. Bobby has since done quite a bit of other work on this problem, but I think computationally, Bobby, your solution is less than Cinco, but not like, yeah. What the student did is he wanted to take a jump step from Lee and Brokenbow, add fractal theory to it, and generate the fractured well problem. That's what he was doing. So here's his result, and what you can see is it matched pretty well. Now I cut out a lot of the slides here, and I didn't want to bore you, and I promised to only do 6 slides per student. There was a huge calibration sequence here, okay? But it worked.
You ran it down to 0.6, FCD of 0.6?
Yeah. Mm-hmm.
Right.
The difference, though, was that the Cinco model takes about a day and a half of continuous.
Well, there's another issue, too. The Cinco main model is a loss transform solution. And for very, very low conductivity fractures, the addition number of the coefficient matrix becomes singular.
Yeah.
So you can't even compute it with it, especially at early times.
But even without this, the important thing is just to run the Cinco model takes a day and a half on a laptop, on a desktop.
It depends
This
on
one here is a matter of a few seconds, that's it.
It depends on the conductivity, for instance, conductivity as well as the time, but it can be as many as 20 to 50 elements. once you get to the point where you have to use a whole lot of elements, then you reduce the distance between the midpoint of the node, the cell, the element, and the node of that element, it becomes singular again.
Yeah.
There's no win situation.
So let's just cut to the chase. Bobby's been working on this problem for 25 years. One day he's going to get a crown, and it's going to say, you know, I figured out, Bobby, you've even got a proprietary solution where you did mean value theorem, and there's I guess it's been patented by Schlumberger or whatever, but it's almost a direct solution for this problem. There's a variety of different ways of solving it. Again, this was an academic exercise, but what we wanted to do was demonstrate this concept. So then we did the derivative, and so it's not good enough to match the pressure drop. You have to also match the derivative. Bobby's looking at that going, that looks pretty good. Yeah, we'll wait till the next slide. Okay? So the next slide is not log-log, but Cartesian in the y-axis, and there's your drift. Okay? I told you it was a curve fit or a calibration, and that's what's happening here. So the part that's matching the trilinear flow part is excellent. The part that gets into the fractal, which is represented as pseudo-radial flow, has a problem. You knew this was going to happen. But the purpose of this exercise was to demonstrate the concept. And again, don't get me wrong. I'm very pleased the student pushed this. I'm very pleased that that we sponsored this work, because it may actually have some. This could one day be used as a proxy model for the horizontal multifrac and save us a lot of pain and anguish, just as an example.
See that what is happening is that he had to rely in the end, especially for that horizontal part, on some kind of curve fitting approach, and it worked well up to a point. I mean, the guy was doing was working on a master, so he had to get out. But this was more than enough work. But certainly he's pointing us in the right direction.
Well, if you saw the calibration curves, and again, I'm sort of apologizing I didn't show them. A couple of them were very uniformly behaved, and a couple of them were not. And what you're seeing here is the ones, there were multiple parameters being calibrated. A couple of the ones that were not, that's where this is coming from, I'm sure. Okay, the last slide in this, Bobby, this is going to look very familiar to you, and that is the dimensionless pressure and the pressure drop, or dimensionless pressure derivative error. This is the L1 norm, and you can see how it varies as a function of conductivity. Our little trick solution works really well. It actually works better than his derivative solution, and of course ours is direct, but ours is also a calibration. So, and I'm sure your other solution would probably be better than this, but of course it would be more computationally intensive. And for the life of me, I can't remember why we were having issues out here, because we shouldn't be, but it may have been an artifact of how we were doing something, because anything for greater than 100 conductivity is irrelevant. That would be infinite, so it wouldn't matter anyway. So directionally, exercise-wise, this was a nice little exercise. He proved that his point, and he went on to the workforce. So interesting exercise. What does it mean for us in the future? It could open the door to people doing other types of proxy models for this, but it has to be calibrated. That's the only thing I would add. George, you want a final word on this one?
No. I mean,
okay.
Well, actually, just a comment that it's one of these cases where you feel so lucky to have learned from the students' assistants. Initially, I was not sure that it would lead to much, but he proved us wrong. As I said, we was wrong.
The next student was working on something that wasn't directly related to geomechanical aspects, but I wanted to share this with you for those of you who work in rate performance and so on. I'm only giving you a snapshot of this. He did other things as well. I will make sure that, Matt, if you remind me, that I'll make sure that I put all the theses for these in the same area on ours, and of course you can put them on yours. They're on our public sites now, but they need to be in a place where you guys can get to them. So how many of you have used the Doung method for reserves? Okay. So the Doung method, my personal opinion, is a chronic overestimator. It can't be an underestimator by the formulation of the problem. And so I debated a long time before I let a student do this, but essentially what I've done here is I've let the student put a tail on the Doung method, so a terminal decline tail, okay? And you're going, well, that's clever. Yeah, I know. But I swore I wouldn't do this. Why would I not do this, David? Because now I'm changing somebody's model, and I'm making it work where they didn't. And he pointed this out. You know, I'm not saying anything that isn't known, but when you modify someone else's model in order to achieve something that they didn't envision, it's a little bit, kind of, for me, a little bit of a corruption. But we decided to try it. And so there's two models here. One is the logistical growth, and the other is the Doung model, and we've modified them in two different ways to have a terminal decline. This will be a very fast presentation. What do you think happened? It matches much better.
Get a good fit.
It matches much better. And characteristically, that may or may not mean anything to you guys, but what I spend my day doing is arguing with people about models and extrapolations and everything else. And you know, do I lose any sleep over model X versus model Y versus model Z? No, because I look at them all diagnostically, and I'll explain that in a moment. This is the other variation. There were two formulations of terminal decline for Doung's method. This is the other one. And then the final proof is down here. And you can see the rate profiles. The black rate profile down here is the unconstrained version, if you want to call it that, of the Doung method. And then you can see the constrained version of the Doung method. You can see the D parameter here, and then the B and the beta parameters here. So, and of course, I apologize, the rate function arrow should be going back this way. And then, of course, there's all the different models out here. But the key here really is this behavior right here, and then applying a terminal decline. And, you know.
Did your research ever come up with some guidance on parameter M?
On
Parameter M.
The way we do it is not shown here, but we have a calibration plot for that, or I should say a diagnostics plot for that, where you estimate M from certain behavior, and then you work back and forth between these two plots until you're constraining it. That is a really good point, because the way that particular model is applied, a slight change in one thing or another can cause a dramatic over prediction. So, great point, Bob. But these are obviously simulation runs where, you know, that we used in the, oh, sorry, these aren't simulations, these are just model runs. But we did do a bunch of simulation runs where we validated this against simulated data as well. We also did some field data. I'm really uncomfortable talking about this, as you can see, because it's the first time, we didn't write a paper on this, just a student has a thesis. You know, I don't want you guys to think that I go around tweaking other people's models. We did this, you know, to demonstrate a point. And it was to demonstrate that the Doung method needs it.
Everybody accepts that Doung's overpredicts. I've run across it for a long time.
Well, I wanted to put out there in a public forum, which is the thesis, that, you know, it can be fixed. Just like the stretched exponential can be fixed. You know, the stretched exponential fix came from observations. The Doung method fix came from observations. You know, it's there. We imposed the observation onto the relationship, but it can be fixed. And then the so-called logistical growth model. And the logistical growth model has a very similar characteristic to the stretched exponential and to the power law exponential, both of which all of which seem to come from some sort of family of multiple exponentials. But The modified logistic growth model is the logistic growth model is a population model. It's been used in all sorts of statistical analyses for 80, 100 years. There's another model, David, remind me, Weibull. The Weibull distribution model is analogous. It's not exactly the same, but it's analogous to the logistical growth model. All of these are unconstrained population type models. So again, we added a terminal constraint to it. This is the first formulation, and then the second is a little bit different. But again, we're applying this this D as in dog logistical growth model as our terminal extrapolation point. So. And like the other one, you can see that the logistical growth model is in black, and it comes down like this. There's actually an artifact for the second one where it actually goes over and then back down, and then for the first one, which is just a terminal decline, it comes off of that. You'll notice that these are exponential-ish, so the goal of this was to tie this back. I personally can't tell a lot of difference between the unconstrained logistical growth model and the unconstrained stretched exponential model, but we wanted to go on ahead and include this as well. And again, I promised you this would be a really short presentation. This is essentially it. So, and you're wondering, how does that relate to this project? This project was to understand fundamental flow behavior, to try to characterize the effects of things, and this is definitely what's observed in practice, so I thought it was justified. And then right before the break, we have Mr. Broussard. Now, we already went through the slot drill, and we already talked to Mr. Dustbuster about how he's going to get rich. Okay? Perfect. And the slot drill idea was trying to overcome the limitations of the horizontal multi-frac, which are water usage, expensive stimulation, etc. Well, we got tired of waiting for the world to come to us, so we sat down with this student, and this is another student that George really brought out of his shell. He was an outstanding undergraduate student, but kind of wasn't sure about his creative element. You'll hear me say this, but he's heard me say it to his face. But he did a phenomenal job on this problem. This problem is using a radial composite type concept for representing a horizontal well, and then looking at changing the variability away from the horizontal well in a particular pattern. Now, I chose the power law permeability distribution. So the permeability does what? It decays in a power law fashion away from the horizontal well. That is the most conservative profile we've come up with. Exponential or linear would be much more favorable. So this would be the low end of performance if you could create that. Now, here's the question, Stuart. How are you going to take a horizontal well and create a radial distribution of permeability away from it? Herb?
That's right.
Okay, very good. Mark? Anybody else? Do you guys like the movie Madagascar? No? Remember the penguins? What was
I
the...
remember their accent.
Yeah, what was Rico's, the one that couldn't speak? All he ever said was kaboom, kaboom, kaboom. Yeah. Did you do this with explosives? We don't know how you're going to create this. This is sort of our slot drill. We don't know how you're going to create this. Acid's probably not going to work because you'd have to inject an ocean of acid, but directionally, the concept would be right because you're going to have a die-off of permeability, but you're probably going to have to inject an ocean of acid. Explosives, maybe. Anything else? Halliburton, Pinnacle, Halliburton, Schlumberger, Orlab. Well, you guys got to have something in your skunk works.
Fiber-sized trucks.
Sorry, fibers? Yeah. I hadn't thought about that.
Well, I can see how you do it in like a heavy oil reservoir. If you're heating it, you're actually producing conductive fluids, then you'd have radial permeability distribution.
Okay.
In a conventional reservoir, and I don't know.
You mean a reservoir with integrity?
Yeah, with competent formation.
That's a really good point. Maybe we could do it with heat.
Heavy oil.
Well, actually,
Then you could actually.
Maybe we do it with heat and cold cycling, you know?
It's not necessarily permeability, but it's mobility reduction.
no, in an expanded sense, yes, because one of the things I was thinking about is if you put liquid nitrogen, you know, that could be doing something like that. I mean, but anyway, again, you'll need the notion of liquid nitrogen for that too, or liquid CO2 for that matter.
Anything else? We're way ahead of our thinking here because we can't deploy this.
We have a solution in search of a problem, right?
Well, this is being recorded, George. I didn't say it, you did. But the reality is he's right.
I think you could do it like in a SAG-D project.
Sure. And maybe this has pseudo been studied before. You know, what we really need to do, this is relatively recent work, and we let the student go off to Chevron and, you know, he's in Bakersfield and his brain's atrophied, so maybe he'd like to continue working on this. I don't know. Maybe somebody else would like to do it. But I think we need to evaluate all possible realms of this. But I'm sure in your lives, those of you who are simulation people have generated things that the company didn't have a use for. And, you know, we're sort of in a similar situation here that we're generating a solution in search of a problem, as George said. Will we see something in our lifetime that generates this?
How long do you plan to live?
My aunt died at 101 last month, so
the answer is
I'm planning on getting there.
Oh, by the way, you know, mentioned things about myself, but I looked up Tom Blasingame, and he's the son of, or the grandson of the oldest living cowboy.
No, he wasn't a relative. We might have been related, but I never met him. Good point. Yeah, thank you. Yeah, he's dead now. But this aunt, her secret was she had multiple cases of Coca-Cola next to her refrigerator. She drank a 6-pack a day. And yes, everybody always asks, well, how were her teeth? Her teeth were fine. She kept them in a glass. They were perfectly all right. Okay.
Bourbon too, or am I wrong?
Oh, she never drank, and she never voted Republican, George. So there.
She never voted Republican?
No. East Texas. So
could you
Yellow dog, Democrat.
Could you do this inside of a fracture by gradually changing the sand?
Dr. Balco's done that. He has another solution that he and a graduate student and Dr. Gildine produced. If you want, I can direct you to that. There's an SP paper on it. We actually took a lead, and Dr. Balco worked with the student and with us a bit on this. But then he went off and did the solution you're describing, which is a varying permeability solution for fracture well. But what we wanted to do right here was just say, okay, poof, there's an instantaneous cylinder of altered rock. How's it going to produce? Okay, Craig, I'm going to give you first option because you had sort of last option last time. Is this going to be competitive with multi-frac horizontal well?
You can get the permeability distribution out just far enough, maybe.
Okay, so let's say, and you're going to see that we chose relatively short lengths, but the reason we chose relatively short lengths is because we don't know what this thing's going to do. And so we chose 25, 50, 75 feet, okay? So let's say that we choose 50 feet, all right?
So we used to cavitate coal bin.
Right.
So if you choose 50 feet, I choose no.
Okay. Next. But both 50 feet fractures and 50 feet permeability radius.
Oh, if the fractures are equal and the permeability radius is equal, then it depends on what the permeability is.
Correct. But so now you're changing your answer. Is that your final answer?
Well, you didn't tell me that I had to have really short fracks. I don't believe we have 50-foot fracks.
Well, let's say we have 50-foot prop fracks. I mean, we can go out to 100. We can go out to 150 feet, and the scalability of this would be, I would argue, be the same. But
if the prop fracts and the permeability distribution go out about the same distance in the reservoir, then I think the answer could be yes. Depending on
Could be yes. I like that. Could be yes. Should be no, but could be yes. I like that. Okay. Anybody else want to comment?
Well, if you've got a cylindrical volume of reservoir around this horizontal wellbore that has higher permeability than just periodically spaced vertical fractures, it's got to produce more. Well, you got a higher permeability region around that horizontal wellbore.
Yeah, except that we chose the most conservative permeability region we could find.
So it's not higher permeable, what you said?
It is, but it's not linear and it's not exponential. It's logarithmic. I mean, it drops like a rock.
I don't know, that'd be questionable.
Oh, well, let's see.
I thought so much is higher permeability all up down through the cylindrical volume.
It is. It's cylindrically distributed, but it dies off quickly.
Wait a minute, I'm confused. Which direction is it? Radial?
Well, just give us a second. Give us a second.
Normal to the wellbore?
Yeah.
Or along with the length of the wellbore?
It's normal. Well, just give us a second.
Okay.
Okay, so we'll jump through this slide so we can get to Bobby's question. This is what it looks like.
Yeah, that's what I thought you were describing.
Yeah. So there's an inner dimension and an outer dimension. And for simplicity, we treat it as a radial composite system, but the inner dimension has a permeability distribution. A very aggressive, declining permeability distribution.
When I think about the SAG-D projects.
So if you go back, this is what the permeability profile looks like as a function of radius. It drops off dramatically. It's power law. It's not exponential. So it decays like a fractal type dimension, I guess you'd say. Comments, thoughts? Anybody want to change their vote? Mark?
I think it'll be as good or better.
Sorry?
That's good.
I might have chose the ones that look that way. Okay, so again, the student, excellent student, he went on ahead and generated both analytical and numerical solutions. This is his analytical solution, and it looks quite familiar, but this is a rate decline case for a radial system with this permeability distribution in it, and you can see that it looks familiar. You can see the influence of the permeability distribution over here. This would be your maximum permeability value and your minimum permeability value, and then its distribution across the page. So let's cut to the chase. Try to focus over here in your comparisons with these two, because this is rate, and the case is XF equals RS equals 50 feet, and the fracture conductivity here is 10 millidarcy feet, and the dashed lines are the radial system, and the solid lines are the multi-frac horizontal well. The yellowish line is 100 fractures, red is 75, blue is 50, and green is 25. So I've varied the number of fractures here. And again, I might have biased my selections a little bit, but what do you think? In theory, we could, or sorry, maybe not theory, but in sort of concept, we could generate a similar behavior with this radial permeability distribution as we do with a multi-frac horizontal. Of course. And I chose, like I said, the most conservative. I don't know what it's going to, if you're going to have an event at the wellbore, my contention is that it's not going to propagate very far. It's not going to be very effective. But maybe I'm wrong. I mean, George and I went Fifth City by way of Knuckle Junction trying to describe how this would look. I mean, we had a concept at one point where you would create this and then you'd go back and inject sand, a sand slurry into it to try to puff it open. Something like that might be really interesting, but you got to create the thing to start with.
I mean, people are looking at trying to do things like this with control burn explosives and things like that. The issue really is how far can you're still trying to create fractures, hydraulic fractures in a sense, and how far can you go out
ironically, this may be one of the most important things we talk about in this project because we've identified that we can have a target of achieving a production profile, but we have to figure out what the mechanism is. You know, if I were a person sponsoring this kind of research, what I would want to know is whatever we deploy, I would automatically assume we're going to lose the well and we're going to have to re-drill it, but maybe that's not the case. But everything I've seen from controlled burn propellants is not enough energy. So there has to be a difference between, you know, classified military grade explosives and controlled burn propellants.
You know, some time ago, they may still do it, but there was an acoustic device to try to reduce the damage in wellbores. But I was thinking that if you could actually resonate the rock with an acoustic device, it wouldn't take that much energy to generate some fracture.
There's that one, and then there's another idea, and I'm drawing a blank. It was a guy that was at Texas Tech. He had an electrostimulation device that created radial fractures in a block of cement, but I don't know if you can deploy that much energy. I kept thinking it'd take a Class 4 nuclear reactor to generate that much energy.
Well, one would argue that explosives aren't the way to go, because they'll compact the rock more than they'll fracture the rock. But I guess it depends on the the time domain of that.
I have been hesitating to speak about this, but he just said some key words over there. I don't think I'm violating any national security issues here, but we are involved in some of these studies, and you're absolutely right. The problem is, with what you're describing, is that you're trying to create fractures through compression. This is not the way to go. Actually, the most effective way is to create fractures with tension, because the tensile strength is much, much lower. So to make a long story short, there is evidence from subsurface testing of bombs, nuclear and conventional, that it is this power law that Tom has been talking about. The most effective thing we could use right now is a new generation of explosives, so-called thermobaric. In essence, these create, say, vacuum. Okay, I cannot say much more about those, but you're perfectly right about this. Compression is not the way to go, and certainly not in shales, which are relatively soft. Okay, but we are working this with Lawrence Livermore National Laboratory, and that's what they do. They just test some of these things, and we believe that there is a possibility, a strong possibility there. However, I will second Tom's statement that propellants control burns. We don't have enough juice.
And we know there are people that are marketing this. Halliburton has a solution for near well cleanup or near well behavior, but they've never tried to market it as a fracturing, to my knowledge, surge jet. Yeah. And then there's other people that have written public proposals about wanting to use propellants. We're aware of all this. You know, what we're basically saying is, if you can do it, then this is the kind of performance you would expect. And, you know, quite frankly, we would like to pursue what George just spoke about, but it's extremely sensitive in terms of how people view a technology like that.
And I would like to add, the sensitivity is not coming from the application of a defense technology. I mean, we're both ourselves and they're open to that. The hesitation and difficulty comes from lawyers, because the issue is that they want complete indemnification if anything goes wrong in the field, and it's a situation where, you know, it's unacceptable to at least one of the parties that we discussed. So we had a situation where this was approved, the money was ready, waiting, and then the lawyers killed it, unfortunately.
This is one of the places where the government needs to sponsor something, because until there's a demonstration, none of your companies are going to buy this. We know that. This is a case up top where you see that the 50 foot, and then it's a low conductivity fracture. So actually, the radial case does better, but of course you can also formulate it to where the horizontal well case does better than the radial. But the point is, there's a variety of possible solutions. It's on the same order, so if we could generate this, then maybe. And this kind of combines with the work on the fractals. If we could combine these two into a proxy for a horizontal multi-fracture, it might help us to come up with some different rate decline models and that sort of thing. But it's definitely time for a coffee break. It's definitely time to sort of put all this behind you for a few minutes and think happy thoughts. So we'll reconvene at 10:45. Donuts in the bag, some healthier donuts. We've got plenty of soft drinks, coffee machines over here. Restroom is right outside the door. Be sure you go in the one with the little stick man on it, not the stick lady. And we will reconvene in 17 minutes. So.
How you been, Scott? I haven't seen you in ages.
Miners have these gigantic excavators. 6 foot size, as opposed to going 6 inch.
It would. You know, one of the companies we wanted us to try our coal mines. In theory, we could just continue to under-ream or over-ream.
About a year and a half away from 85. Yeah, I
That's not bad, because you could create a device that would open up to follow the original formula.
So your question, what it costs?
No, but if you're following this, drilling time reduced from 30 days to 6 on most shale wells. So now 80%, 75% is cost of stimulation. You can go back and just slowly work your way back and forth. I don't think a lot of people are going to jump at it.
I guess the thing about it is,
We call it the herb method.
how much more
Right.
No,
Anybody needs internet, you've got wires here.
Razor blades get expensive this morning. We got you up to already.
You know, I'd wear a coveralls.
Got you up to. That's it.
Have you heard of little steam wells stimulated by the gas gun?
No, that was at Surgeon, the Halliburton tool. At least that's the way I understand it.
I don't think Halliburton.
Well, they have a tool Mark might know. Surgeon, that product line.
Is that the one that,
Sure, Jim.
Yeah.
Halliburton's got stim gun, is that right? And I sat through a presentation last week. One of the guys from, I don't know if he was, I think he was Sandia. He did a lot of stuff at the multi-wall when they were doing some of the control burn explosive. He's got his own company. And he was talking about all this great stuff for unconventional. So, how long? Yeah, I mean, it's a whole, that's the thing.
that's like the hydraulic system.
What we keep finding is just, you have to find something that can deploy on the energy.
I mean, you could do that with hydraulic, but what you're trying to do is stimulate,
Pulsation.
that there is a resonance in the vibrate.
Every time I look at all these new techniques, I always come back to the one question we still argue about, is how effective stimulation to do it right now. I mean, everybody will jump up and you'll get the 2 camps. Actually, you'll get mostly 1 camp. Right? So we have to hope that what we're doing now really sucks. These other things to really work easily. Because if we're actually doing not such a bad job, then it's going to be hard to find a good substitute.
Cost-effective.
The cost-effective. Oh yeah, you can. Yeah, because you look at the area. That's like the slot drill thing. You look at the area. Well, if you look at any of the fracture mechanics, it's tens of millions of square feet. Typically, and maybe even 100 million square feet of surface area. But only 10%. That's good. Okay. Now you get down to an order of magnitude you could put. But if 60 or 70% of it, or all of it, is actually contributing somehow, then it's tough. It's tough to find the silver bullet that fixes it. And that's another thing that you guys.
Well, we're on coffee break right now, but what I'm really believing is that it probably is that all of this is contributing, and that we don't know where it's coming from. And that, because we know that size of the job matters, we know that structure of things, how you column, how you do this, how you do that matters. And all you need Diet Coke.
That's what I'm looking for.
I can tell you.
And I think that's the real scary part, because if most of it is contributing to some degree, then we might be reaching out a little further than we think. It might be very heterogeneous in that. It's harder to.
Okay, so tell me what keeps you up at night. What keeps me up at night is right now recovery. Probably only 5 to 7%.
I think what amateurs do.
Yeah, let's make it.
If our completions are as good as they can be, how come we only recover 10%?
Like amateur,
Yeah.
Gas.
Gas is easy.
Oh, let's go higher.
It's still not a
significant fraction. You know, and so what do we do? How do we pay back?
He had a basic
Well, we didn't talk about it here, but in our discussion, I think we're going to see enormous bursts of just sort of gas and maybe condensed liquid, if you can generate it. And see, that's the unintended consequence, I think, of being able to generate a rubble zone or something like a rubble zone, because I think we'll see enormous flush production capability. Now, I know you guys are going, oh, here's the dream, but I think if you cause something like that, it's going to stay much better.
I've seen other people do models of that.
Did that coal. We did cabbage.
I think the fundamental difference in coal is that a lot of coals are already naturally fractured. Well, naturally fractured in a sense. So if the shales we're dealing with really aren't naturally fractured, where all these natural fractures are already contributing, then it's a different story. You don't have to create the system. You can just connect into it like you do with the coal.
I mean, guys, I'm sure you remember this, but the guys who worked on coals that showed that as production increases, variability increases, you know, and they were trying to propose that for shales. And, you know, we look back at how much smarter we are than we were a couple of years ago. I don't know that we can take shale and coals and make an analog, but I'd sure like to see us bust something to smithereens and at least test the idea.
We've been there, done that.
Oh, his buddy wants to. Yeah.
Nuclear track?
It's not new. It's not
We
new.
did that. We did that, and the production was phenomenal. The only problem was the gas was radioactive.
Yeah, you talk about the environmentalists getting off about fracturing. You know, how many nuclear bombs can you set off before they start getting
It was in the late 50s and early 60s. It was fantastic. It came out like, you know, oodles of gas. That's what the problem.
Oh, damn. You're okay. X, Albert, now.
It all depends what you mean by this.
We believe we do that by superfrac, so yeah.
Right, so I look at seeing where to go in like full cross section. EOG wells before we
If you'll give me your business card or send me an email,
except on the same.
I mean, you got it. Actually, it's
It's
more
the radial pattern.
coastal body.
Just better for you get the same recovery out of it, less volume.
Well, it depends on the initial state of the rock, of course, and the initial stress distribution and everything. But the evidence is you basically get quasi-planar structures, not even the drilling pattern. So that you need something far more to create gravel zones. You need a lot of energy for that. And actually, one of the things that we're working on is the basic idea of not just fracturing, but also dislodging the system. Because then you don't need anything like proppants. You need to keep the fractures open.
But if you put them closer together, you're forcing that fracture energy to stay closer. So you put the same amount of energy, you have to fracture part, the smaller part is the same energy that you put in the bigger one. That's got to be, I think that has to be.
I would think each well would get more near level surface
Correct.
area.
And less length on your fracture.
Well, it's different than shattering. I think you're going to have stress
Well,
shattering.
So maybe more near level or sort of.
It's not really shattering, it's just confining the fracture.
We know they have there is interference. We'll look at that. I mean, maybe people will wave their hands and say they do, but yeah, I think that, we know that cracks interference.
People say, well, we get fracture interference, but no, not interference.
You do get fracture. You don't care. It's like two wells. One or the other is getting there.
Well, I think you do get production interference. People just don't know how to diagnose it.
If you show, if you got two wells that are too close together, you shut them in,
I mean like long term. You can see it short term. Exponential decline when they get hit. I mean long term or the effects of.
I think the tighter you space, the more actually cover each well individually. So your capital efficiency is less. If you can drill wells cheap, it's you can't drill wells cheap.
Not anymore.
In fact, our optimum well spacing is to drill 0 wells.
Eagles are the same way. Places are off and off way out. I think the last I talked to one of the operators there, on some of the gas wells, it was costing about $6 million